What's up, stats? Welcome back. I'm Mr. Carlson, and this is C-Squared Mathematics. We are going to be learning the normal distribution today for our unit in statistics, so 5.1 normal distribution, and we're also going to be learning what we call the empirical rule, okay, and how it relates to the normal distribution. So as you can see, I have this set up because I'm going to be using Desmos a lot. Obviously, I'm not going to be using the binomial here or the geometric or Poisson because that's what we did the last unit. But what we will be doing is what we call the normal distribution here. Okay, we will be doing that a lot. So that's why I have it pulled up, because I'm going to go back and forth between Desmos and our slideshow. But before we get started, you guys do have a homework quiz. All right, so make sure you pause the video if you need to. Go do that homework quiz. It is 5 questions, 20 minutes. It should not take you more than 10 minutes, honestly, because it's that simple. It's all over vocabulary and everything. So make sure you complete that and then come back here and start your notes for today. You can print out the sheets from Google Classroom if you need to, the key or the 5.1 sheet. By all means, do whatever you need to, print it out, and then start on 5.1, okay? So 5.1, what are we going to be learning? We're going to be learning how to find areas underneath the standard normal curve using probability distributions, normal probability distributions. So I'm going to teach you what that means, but first we need to know exactly what normal probability distributions are. Like, what are they? Well, they are probability distributions, which is why they're labeled over here on Desmos with the other probability distributions. They are probability distributions, okay? So since they are normal distributions, are probability distributions, they're going to be acting almost just like what we did with geometric, binomial, and Poisson. Like, they're going to be very similar, and we're going to type them in very similarly how we did those. However, the difference is they are continuous probability distributions. They're not discrete. So these first three are discrete probability distributions, whereas the normal distribution is what we call the continuous distribution, where it continuously goes into decimals and fractions and so forth. Where discrete, it's like countable data, 1, 2, 3, 4, 5, whole numbers. Okay, normal distributions will be like, yes, countable data, but it'll also be like decimals, and we'll get a lot of decimals with regards not just to probability, but we'll also get decimals with regards to like plugging values in and so forth, or getting values out. Okay, so feel free to watch this video. It's on the crash course. I posted it here so you can click on it if you're following along on the slides. You don't need to watch it by any means at all, but it's just maybe a helpful thing to get to know what normal distributions are. So many real-life data sets have distributions that are approximately symmetric and bell-shaped, which is exactly what the normal distribution is. That's what we call sometimes a bell-shaped curve when a teacher curves the test. The following empirical rule can help you see how valuable the standard deviation can be used as a measure of what we call variation. So I'm going to show this on the screen. Don't freak out. But this is what we call the bell-shaped normal distribution. What is this? Like, what really is this? This is what we call the bell-shaped normal distribution. What this is really this shaped curve, so this bell-shaped curve right here, okay? And I'm actually going to pull this up real quick. Yeah, let's do that. Let's zoom up. So this is actually the bell-shaped curve, as you guys can see. It's very similar, okay? So you can see it, but it's very, very similar. This is what it is, all right? Now, what this actually tells us is depending on how far we go from the mean, the middle data, how far we go from the mean is the variation, the standard deviation. And it tells us what percentage that we have in that area underneath the curve, depending upon how far we go from the mean. So this right here, this X bar, usually we say the mean is mu, and we will still use that, yes, but now we're also going to be saying that the X bar is the mean. Okay, so they will kind of be used interchangeably, so I just want to make sure you know that. Now, what is this? The S is going to be my standard deviation, so I'm just going to say that, standard deviation. Okay, and that's what you see here, the S, the 2S, and the 3S, so standard deviations. So now, what is really happening here? Well, this is the mean in the middle. Now, if I move one standard deviation over to the left and one standard deviation over to the right, what this equals is a total of 68%. So that is what we call the empirical rule. I'm going to show you what that means in a little bit. But it's what we call 68%. Now, if I move 2 standard deviations, notice the 2 there, 2 standard deviations, and when I add up 13.5 plus 34 plus 34 plus 13.5, when I add all of that up, so when I highlight all of this, when I want all of this data right here, okay, when I want all of that, I get 95%, okay? Now, what if I want 3 standard deviations, so way at the tips here? What that means is I'm literally getting all of this data. I want all of that data here. I know I'm not really scribbling it completely, but I want all of that data. So now really what that means is this. If I want 3 standard deviations right here, I technically add 2.35 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35, and then I get what we call 99.7% of the data. Now, the reason why this is probability is because look at this. It's percent, right? We're going to be using that a lot. Not really today. We're not going to be really going into probability today. That's going to be more reserved for 5.2 tomorrow. But this is still percent, and so it's still probability. But we can also say that this is area. So this right here is what we call the area. And this whole thing, 3 standard deviations, all the way out here, all the way out here, that's what we call 99.7% of the area. Okay, so the area is roughly 99.7% covered. Okay, now this is a helpful tool, right? Because now what we can do is actually use problems and solve simple problems using what we call the empirical rule. Okay, so I'm going to actually go through a couple examples so that it actually makes a little bit more sense. But before we do that, here is the actual definitions. So from the 68, 95, and 99.7% rule, that's what we call the empirical rule. The data sets with the distributions that are approximately symmetric and bell-shaped. The standard deviation has these characteristics. 68% lie within 1 standard deviation. 95% lie between 2 standard deviations, and 99.7% lie between 3 standard deviations. Okay? So this is just going to be put right here just so that we can use it, but we're going to be going through example P. So example P as a prerequisite thing to just understand before we get to normal curves. Let's get to it. In a survey conducted by National Center for Health Statistics, the sample mean, okay, was 64.2. So what is that? Well, first of all, I'm going to actually build this. Okay, I'm going to build this. Just a normal curve. Oh, man, that looks awful. Can I erase? Can I start over? Because that looks really dumb. Okay, that looks a lot better. So normal curve right here. Now my mean was this. So that's technically like my x bar or my mu. So they mean the exact same thing. So this is 64.2. Okay. With a sample standard deviation as 2.9 inches. Okay, so what that means, guys, is this. If I add 1 standard deviation over, okay, what it means is I'm adding 2.9 inches to 6.42. So if I add 2.9 here, what I get is 67.1. And I can also do it on this side too, if I wanted to. So I can now subtract instead of add. I can subtract now. So now what I can do is subtract. So 64.2 subtract 2.9. So if I subtract 2.9, what I get is 61.3. And I can do it again and again. So if I subtract again, what I get, 61.3 subtract 2.9. What I get now is going to be 58.4. Does that make sense? I hope. And I could add on this side too, so another 2.9. If I can add another 2.9 to 67.1, what I get is 70. Okay, so that's sort of how you build your curve. Now, what it's asking is estimate the percent of women whose height is between 58.4 and 64.2. Well, look, I'm going to do this in green. 58.4 between 64.2 is what I'm going to highlight in green. This right here. So I want to know all of this. Okay? I want to know all of this. It's equivalent to saying this. I want to know all of that. So if I look back at my actual curve here, what I'm given, I want to know all of that. Because right here is where 58.4 is. This is 61.3, and this is 64.2. Right? Right here, and right here. Correct? So similarly, look at mine that I built. It looks exactly like that. So I want to know all of this. I want to know all of this area. Okay? So how do I know all that area? Well, look on my graph. Look on my graph. So my graph says this. 34% is that little section, and 13.5% is that little section. So all I have to do is take 34% plus 13.5%. That's it. And what I get is 47.5%. And then boom, that's my answer. Okay? And that's it. That's all. That's the empirical rule. Not too bad, right? You're adding and subtracting. Okay, so let me erase this and let's go to another example. So now the mean value of a land is 1,500, so that is my mean, with a standard deviation of 200, so that's my S. Okay, now we want to go from 1,300 to 1,700, so I'm going to build my curve. My mean is this, so 1,500. Now my standard deviation is 200, so that means I want to go above, so 1,700, I just add, and then I also want to go below. Okay, so that is 1,300. And that's what we want, right? We want between 1,300 and 1,700. So really what I want is all of this information. So I want all of that, what I'm kind of shading here. I want all that. But if we look at a graph right here, what I really want is this stuff. That's what I want, just like I want this. Okay? So now the thing is this, okay? This is 34 and that's 34. This is 34%. This is 34%. So what is my answer? Between 13 to 1,700, it's 34% plus 34%, which in this case, our graph already tells us it is going to be 68%. That's my percent of farms whose land and buildings values are between 13 and 1,700. 68%. Not too bad, right? Not too bad at all. So let's continue. We're going to kind of take a break with the math right here and kind of go through a little bit more vocabulary on the normal distribution. But I just wanted to show you that because that is going to be actually used. That's actually going to be used throughout the lesson. So let's go through some vocabulary, properties of normal distribution. Let's go through a definition. What is the actual normal distribution? Well, it's a continuous random variable that has an infinite number of possible values. A continuous random variable and probability distribution that has a continuous or an infinite number of possible values. Okay. The normal distribution is literally the most important continuous probability distribution in statistics, okay, which is why we're learning it. And I already told you it's a probability distribution, but it's a continuous probability distribution. So normal distributions can be used to model many sets of measurements in nature, industry, and business. For instance, the systolic blood pressures of humans, lifetimes of plasmic televisions, and even housing costs are all normally distributed random variables. Okay, very interesting stuff. So let's get into more of the definition. Normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is what we call the normal curve. It has the following properties. So number one, the mean and the mode and the median are all equal. They all mean the exact same thing. Okay, they all mean the exact same thing. The normal curve is a bell-shaped and symmetric about the mean, which we kind of already learned. The total area of the normal curve is equal to 1 or 100%. So it's equal to 1 or 100%, because if we put in decimals here, then it will be equal to 1, or we can do 100%. Okay? Normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. So it does never actually touch the x-axis, but it will go on forever and ever, which makes it a continuous probability distribution. And then between your mean, mu, and then minus your standard deviation, that's what that symbol means again, standard deviation, and your mean plus your standard deviation, your graph curves downward. Okay, so it curves downward like that. The graph curves upward to the left of that, so it curves upward like this. So follow my cursor on this side. Curves upward, but curves downward right here. Okay, but where the points kind of change, so as it kind of goes from here and then kind of starts to go down, okay, that's where it's called the points of inflection, or inflection points for short. You don't really need to know that much about the inflection points. We're not going to dive too deep into that, okay? So for continuous probability distribution, you can use a probability density function. So that's your PDF. You can use the density function if you want to, but very, very rarely will we use it, if at all. Like even if you look on here, when we start using it, you don't even see a PDF here at all, because a PDF probability density function, because we don't ever use it. You can use it though. The probability density function has two requirements. The total area underneath the curve is equal to 1, obviously, and functions can never be negative. Okay? So what does this actual function look like? It's going to be really odd looking, but I'm going to write it down. It's going to be 1 all over. Oh, let me redo that. I don't want it to slant. 1 all over. It's going to be standard deviation times radical 2 pi. Okay, and then times e, which is a constant. It's 2.71828. Okay, that's what it is. And then negative to the power of negative x minus mu squared, and that's divided by 2 times my standard deviation squared. So your standard deviation is your variance. This is a very nasty formula, obviously. Okay, very nasty formula. Do you need to use it? No, okay? I just like to show it to you because it's very interesting, but you don't need to use it at all, not by a long shot, okay? Not by a long shot, because we do have Desmos and we're going to be using Desmos a lot. But before we get to there, let's go through a little bit more characteristics on what that, oh man, why did I write it down? Let's go to a couple more characteristics, okay? Normal distribution can have any mean or any positive standard deviation. So it can be moved around however you want to, okay? And that's the beauty of it. This can move around wherever I want, honestly. Depending on what I change it to be, it doesn't matter. It can move around however I want. The two parameters are your mean and your standard deviation. So your mu and your standard deviation, there, your sigma. Determine the shape. Those two determine the shape of the normal curve. So if I move these two things, this is my mean right here, 0, and this is my 1, which is standard deviation. If I move the standard deviation to 5, notice what happens. Move to 6. What if I move it to 0.5? Okay, so it does change the shape. Now what if I did 2, 1? Notice how it moved a little bit. Or what if I do 4? Or 5, and then I would have to zoom up into it. Notice how it's moving because my mean 5 is right there. Yes? So I can move it however I want, wherever I want. That's what it means. Okay? The mu gives the location of the line of symmetry, and the standard deviation describes how much the data are spread out. So the mu gives the location of the line of symmetry. So the line of symmetry is this thing right here. So I can move it and the line of symmetry moves. And then the standard deviation describes how much the data is spread out. So now look at these couple examples here. Yes, these are the inflection points, but you don't need to worry about those. Look at the pink line right here. It's the mean. The mean is 3.5 right here. But notice the standard deviation is 1.5. I can go over here and replicate that. So 3.5 as my mean, and then I can go over here and do 1.5. Okay? So that's sort of what it looks like, roughly. So I can kind of mimic it is what I can say. I can mimic it there. Now, notice when I do a standard deviation of 0.7, it actually becomes, but keep the mean, it actually becomes a little bit skinnier. So if I do 0.7, it becomes really, really, really skinny, right? And if I keep the mean or change the mean to 1.5, notice how it just changes a little bit, okay? So yes, you can move them however you want. Now we're going to ask which normal curve is a greater mean and which normal curve has a greater standard deviation. Okay, which one has a greater mean? The greater mean is going to be right here, which is A. Okay, and that right there, your x bar or your mean, your mu is 15. Okay, so A is the answer for that. Which one has a greater standard deviation? The greater standard deviation is going to be B. Okay, because B is just more spread. Okay, now you're not looking at the mean, so you're like, well, that's 12. That's not greater. No, 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 no. You're not looking at that. You're looking at how spread the data is. All right, and so since this one is a little bit more fat and a little bit more like wallow down, that indicates to me about the standard deviation. So it's more spread. How are we feeling about that? Hope we're feeling pretty good. Okay. All right, let's get into a little bit more characteristics about interpreting the normal distribution. So a scale test for New York State grade 8 mathematics tests are normally distributed. The normal curve below represents this distribution. What is the mean test score? Okay, so the mean test score, I don't want it to do it like that. Let's just keep it with mean, with mu. The mean test score is roughly in the middle here. Okay, so it's probably going to be like right here-ish. Like somewhere maybe like around here. Yeah, let's use that. Okay, that's my mean. Now what is that? Well, that is 660 right here. That's 650. That's that's 660. That's 670. That's 680. So what's in between 670 and 680? 675. Sweet. Now, what's my standard deviation? My standard deviation is going to be a little bit harder to find. So what we can do is look at our standard deviations from our points of inflection, actually. These are points of inflection will actually tell us the standard deviation. So somewhere like right here, where it actually starts kind of going, changing. So it's probably like somewhere like right here. And then same thing like right somewhere where it's kind of changing and right before it gets to kind of start to slope down. Okay, and that's going to be right here. So it looks like my standard these points right here is 710, and this point right here is 640. Okay. So since that's 710 and that's 640, and my mean is 675, what's my standard deviation between here and here? Now, this is why the points of inflection are very helpful. Points of inflection, because they actually do help you find your standard deviation. But honestly, we never actually do this, so that's why I don't really care about the points of inflection. They really are only useful for this one thing. Okay. Standard deviation, what is it? Standard deviation, well, all I have to do is take 675 and then minus like the bottom one, so 640, because that's where it hits the points of inflection. And when I do that, I get 35. So that is my standard deviation, is 35. Not too bad, right? Not too awful. So what we learned basically so far is we learned a lot of the normal distribution, how to kind of work it on Desmos a little bit, how to change it from back and forth. We learned the empirical rule so far. we really just learned characteristics of your normal distribution. So what we're going to be learning now, and we're going to be ending it, is what we call the standard normal distribution. This is another video from Crash Course. By all means, I posted it there so you can use it. But what the standard normal distribution is really trying to standardize. Really what it is it's standardizing certain things. Okay, it's standardizing this graph. And so what the standard normal curve is that it makes the mean 0. So I'm going to change my mean to 0 here. And then my standard deviation as 1. So this right here is what we call your standard normal curve, your standard normal deviation, okay? Or normal distribution. Wow, that's supposed to be a normal distribution. So change that to be normal distribution. Okay? Sweet. That's supposed to be normal distribution. So the horizontal scale of the graph corresponds to what we call z-scores. So I'm going to show you what that is, but it corresponds to what we call z-scores. So the z-score, really what that is your value minus your mean all over your standard deviation. And then that is your x minus your mu all over your standard deviation. Okay? So x minus mu, so x's value, your mean is going to be mu, and then that's going to be standard deviation. So x equals value, your mu is mean, and then your standard deviation is your sigma there. Okay? Those are all the variables. Now you want to round to the 100th, so what does that mean? This is 2 decimal places. 2 decimal places. This is how you do it. So what is a z-score? Well, a z-score really is standardizing a test. So when you take a standardized test like an ACT score, it's really standardizing that test. Okay, so it's instead of taking huge numbers, what it's doing is kind of shrinking it into one concise thing. That's really the best way I can describe it. It's shrinking it, those big numbers, because everyone, all high schoolers take an ACT or an SAT, right? So what it does is it shrinks all that information into one little standard normal curve like this, and then you can start performing operations on it, performing probability and finding area and all that fun jazz, which we will do in a little bit, okay? But now there's a difference between a standard normal curve and then a regular normal curve. So a standard normal curve will have a z-score with a mean of 0 right here, and then a standard deviation of 1. Whereas a normal curve, a normal distribution, simply has whatever. It doesn't matter what the mean is. It doesn't matter what the standard deviation is. Okay? So here's some characteristics. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. The total area of a course is 1, just like this. You see that this equals 1, right? Because this total area right here is 1. Okay, we're going to come back to Desmos in a little bit. And of course, there's a picture there for you. This right here, this thing in the middle, this is going to be your mu. Okay? And then your standard deviation is 1. Your mu is 0. Your mean is 0. Okay? And that's exactly what we have here. This is your mean. Okay? Notice how it says mean, comma, standard deviation. So your mean comes first and then your standard deviation. You just plug them in, mean, standard deviation, and then boom. That's it. All right? So let's erase this. Let's get to some more characteristics, some properties. So properties, the normal area is close to 0 for z-scores. That is going to be z equals negative 3.49. So the cumulative area that is close to 0, the cumulative area is close to 0 for z-scores close to z equals negative 3.49. Okay, the cumulative area increases as the z-score increases. The cumulative area for z equals 0.5. For z equals 0 is 0.5, sorry. The cumulative area for z equals 0 is 0.5. So let me say that. So this right here is z equals 0, and that's the cumulative area. All right. And then the cumulative area is close to 1 for z-scores close to z equals 3.49. So what does that mean? That means, guys, right here, notice down here, if you can kind of see, if I wanted to kind of do this, now watch what I do here. I'm just going to do negative 3.49. So that really is where my z is. Okay, this right here, this thing, that's like negative 3 point. Now notice how what I get out is 0.0009. It's very, very close to zero, right? That's basically zero, right? And that's what we say. But I can also make this positive. I can go on the other side. I can click on that and notice how it's also close to zero. That's what it means. So what does it mean? Really, what does it mean? It means that your z-score values, now I'm going to explain what those are as we kind of continue. Your z-score values really only go from negative 3.5 to positive 3.5. Okay, or 3.49, negative 3.49. That's really where they go to. They don't really go past that. So you will never, ever, 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 never, ever, ever, never, never, ever see a z-score that's like 5. You'll never see a z-score that's like 5 or 6 or whatever. You'll never find a z-score that's like 10 or 100. That doesn't make any sense. Okay? So your z-scores will lie only in between negative 3.4 and 3.49. So what does that mean in inequality notation? It means this. So it lies in between these values. Okay? It always has to lie in between those values because that's where my standard normal curve is and it can't move. So whereas your normal curve does move, your standard normal curve does not move. Okay, I'll say it again. Your normal curve can move. I can change the mean, the standard deviation, and we did that a couple times. I can tamper with this. But your standard normal curve, this thing right here, and I'm highlighting right here on the right, that thing does not move. Okay? That thing does not move. This is fixed. 0 for my mean. Standard deviation is 1. Okay? Awesome. All right, so let's actually start solving stuff using Desmos, using the standard normal curve or the normal distribution and solving some math things. Okay? First, I will have to tell you this. There is a table for a z-score. So really, these are the types of problems that we're going to be doing. We're going to be trying to find the cumulative area of or percentage of the normal curve, the standard normal curve that corresponds to a z-score of 1.15. Now, this is what if we were in class, I would give you what's called a normal table. And the standard normal table is what we call the z-table or the z-score table. And that thing looks something like this. Okay, it looks something like this, like a z-score table. I actually have posted it here. So if you follow on Google Classroom right here, it's the z-score PDF. It looks something like this. It's very hard to read and it is kind of lopsided, and I get that, which I posted there just because it's easy to use. You can print it off. It is actually very, very easy to use. I'll teach it to you at least on this first example. But I'm not going to ever use it. I'm not going to ever use it because we can use Desmos instead, and that's way easier, I think, than this. Even though the table itself is really easy and real simple, okay? But I'm just letting you know it's called the Z table, and you can use it however you need to, all right? I'm not going to use it, however. So how do I actually use it if I wanted to use it? Well, I'd look, this is my Z table, and I want 1.15. So 1.15, I would look on my Z table, and I would look at, okay, I would look at 1.1 right here. Okay, I would look at 1.1, and then I would scroll over and find 0.05. Why is that? Because 1.1 plus 0.05 equals 1.15. And so that's what I want. And so now when I kind of triangulate them, I get this area. So what is this area? This area is actually 0.8749. So that is my answer. And this is a percentage. So when I say area, this is a percentage. This is 87.49% roughly. Okay? That's what it really is. I'm going to show you how to do that on Desmos right now. I'm not going to go through the second one because I don't want to go through the table. We're online, so I don't want to go through the table. Now what I'm going to do is show you how to use it on Desmos. Okay, I do want, since it's a standard normal curve, I do want a mean of 0 and a standard deviation of 1. Since it wants to find a z-score, or sorry, it wants to find an area given a z-score, if I'm ever given a z-score, I know I'm going to be using the standard normal curve, which means I'm going to be using 0 and 1. Now watch. I use this right here, okay? The cumulative area that corresponds to 1.5. All I need to do is type in 1.15, and then boom, that's my answer. Now, why do I type it in the max? Because we're automatically going to assume that it wants to read it left to right. So we automatically want to assume that's reading it left to right. That's my point. Does that make sense? That's what I want to know. I want to know if it's reading it left to right. And we're going to assume that's reading it left to right. So that's why you see all of this shaded in purple. And then right here, okay, that is your z equals 1.15. So this is 1.15 right there. Notice how it's below 2. That's 1.15. So it's a little bit above 1, but it's still below 2. That is my z-score, and when it says find the cumulative area that corresponds to that, what you're trying to find is all the area that's to the left of that z-score, okay? And so that's literally it, guys. It's that simple. You're just plugging stuff in. So I'm going to actually prove it to you right now. Let's actually prove it to you and show you really how simple it is. So I'm given these things, right? So this is example 4. I want to find the cumulative area of the standard normal curve. So that means right here, 0 and 1. Okay, 0 and 1. Left of z equals negative 0.99. What do? Well, I go back here. Since I want the curve to the left, I want the area to the left, that means I'm going to adjust my max because we read math left to right. So I'm going to type in negative 0.99, and that is my answer, okay? And of course, that's what it looks like. And that's exactly what I have here, right? Because that's what it wants. So that's really what I want to try to find, all this area. So what is this area right here? That's what I wanted to try to find. This area right here, okay, is this right here, that answer. So 0.16110, or roughly 16%, okay? But either one works. Math Excel will more than likely want the decimal version. Does that make sense? So you're really just plugging stuff into Desmos. That's it, okay? That's seriously it. Now do this one. Left of z equals 2.3. Let's go over here. Actually, let me erase this. And then left of it, so I type in 2.13. Okay, and of course, you'll see something like that as well. It's very similar. Notice how it's very similar, yes? It's a little bit above right here where my mouse is. It's a little bit above 2.13, but right here, that is actually 2.13. Okay, that's your z. All right, and what's my answer? It's about 98%. So this whole thing is 0.98 and then 3.4. Okay, that's my answer. Or roughly, like I said, 98.34%. Okay, that's also my answer. Either one, but like I said, Math Excel will more than likely want the decimal. See how easy this is? You're really just plugging stuff in, okay? So we're going to go to town on this. Let's go to town, and we're going to do this. Now, it wants to the right of. How do I do to the right of? Well, now, if I want to the right of, what it's going to look like is this. How do I do that? Well, now 1.06 is not going to be my max. This is what is going to be my min. So right here, that is 1.06. Okay, that is 1.06. That's z-score equals 1.06. And I want to find, whoa, what was that? I want to find all of this. Okay, I want to find what all of that is in red, where I just did that. So we need to kind of mimic that on the graph. Ready? So we go over here. I want to keep 0 and 1 because it's standard curve. I don't want to do max because if I do 1.06, that's not right. So what I need to do instead is erase this. and I need to make sure that this is my max, so 1.06. Now it actually looks like my graph right here, right? So now what's my answer? I just look on Desmos. So this is roughly, my area is roughly 0.1446. That's my answer, rounding to the 4th decimal place. Okay, let's do the next one. So this z-score equals negative 2.16. I want to the right of, so that means I need to do the same thing. I want everything to the right, everything to the right. Yes? So that means I want to do negative 2.16. Notice how it's very similar, and that is my answer. It is that simple. So this equals 0.9846. Okay, what is this? This area is roughly 98.46%. That's really what it's saying. It's roughly this whole thing in red, this whole thing in purple is roughly 98.46%. That's what it's saying, right? That's the area. Awesome. Okay, so let's erase that and let's go through a couple more. So now what it's going to ask you is in between. In between. Okay, so I want in between these. Well, how do I do that? Well, I can still do it, but this now becomes my min, and this now becomes my max. Same thing here. This will be my min, and this will be my max. Okay, so let's go to town on this because this is the two that I really want to find. So let's just knock them out, okay? So the first one is negative 1.5, and then I want to go to 1.25. Okay, looks very similar, right? So what is my answer? My answer equals 0.8275. That's my answer. Now, oftentimes you may see on Math Excel that it'll read something like this. It can often be written like this. So find the probability of negative 1.5, where z is in between negative 1.5 and 1.25. Sometimes it will be written like this, just FYI. Sometimes it will be written like that. Or like down here, sometimes it will be written like probability of negative 2.16 between z and negative 1.35. Okay, sometimes it'll be written like that down here. Doesn't matter, okay? All you need to know is that's my min and that's my max, and I'm going to do the exact same thing here. Okay, so I got an answer here. Let's get an answer for my second and last one. So I have negative 2.165, and then I want to go over, erase this to be 3.5. Or sorry, negative 1.35. So negative 1.35. Very similar indeed. I look at my answer. What is it? It's that. So equals 0.0733. That is my answer. That's my probability. It's my area, okay, and it's my percentage, okay? Now, if you print off the notes on Google Classroom, you'll see something like this. Okay, this is going to show how to do it by hand. I did not show you how to do it by hand, but by all means, if you want to see how to do it by hand, you can actually print off the notes, and then it will take you step by step on how to do it using your Z table, completely and utterly by hand. But since we have technology, I'm going to be utilizing it as such. Sounds good? Awesome. So I hope that made sense. I hope you're still following along. Let's erase everything and get to the summary. So what did we learn? Interpret the graphs of normal distributions. We also found areas of the standard normal curve, okay? But we also learned the empirical rule as well, all right? So the homework quiz, what are we going to do tomorrow? You're going to do a homework quiz, 2 extra credit points on the homework quiz for 100% on the homework. Guys, please, please, please be doing your homework. Watch these videos. If you need more, if you need like more help, then just keep going through these videos and trying to mimic what I'm doing here on the screen. But guys, until next time, I'm C Squared Mathematics. Be sure to like and subscribe. Peace.